Hello and welcome. Floor and ceiling functions, second edition. Floor and ceiling functions are very important functions. They're used quite a bit in both mathematics and computer science. Let's quickly recall the definition. A floor function is a function from R set of real number to the set of integers. The floor function is the largest integer less or equal than x. The ceiling function, same thing, is from the set of real numbers to the set of integers. The ceiling function is the smallest integer greater or equal than x. Now here's a graph. X is here between two integers. The ceiling function of x is here. Ceiling is here. Ceiling function of x. The floor function of x is here, and x is between the floor function and the ceiling function of x. So in these situations here, when this is n plus 1, then the ceiling function is n plus 1, and the floor function is n. Here are some examples directly from the definition. The floor function of 3.2 is 3, so we're rounding down. Ceiling function of 3.2 is 4, rounding up. The floor function of 3.9 is again 3, that's rounding down. The ceiling function of 3.9 is 4. Now, when you have the floor function of an integer, 5 is 5, and the ceiling function of 5 is 5. The floor function of at 1/2 is 0. So if you have, you put your 0 is here, 1 here, and this is your x is 1/2, and the floor function of 1/2 is 0. The ceiling function of 1/2 is 1. Here is minus 1/2, so you have 0 minus 1, and that's your minus 1/2. Now the floor function of minus 1/2 is minus 1. The ceiling function of minus 1/2 is 0. Look here at minus 2.5 is between minus 3 and minus 2. So minus 3 is the floor function, and minus 2 is the ceiling function. Now here are some important properties. They're really clear from the definition. X is an integer, then the floor function of x is x, and the ceiling function of x is x, and vice versa. And if n is between greater or equal than, if x greater or equal than n and less than n plus 1, n is an integer, then the floor function of x is n. The floor function of x is n, and vice versa. And now if x is greater than n and less or equal than n plus 1, then the ceiling function of x is n plus 1. And this is, you can easily see that this one here, x is less or equal than ceiling function of x, less than x plus 1, and x is greater or equal than floor function of x, greater than x minus 1. Now these functions are called also step functions because they look like steps, and they are discontinuous, onto, but not one-to-one. And you notice here, when x starts from 0, the ceiling function is 0. As soon as you move a little bit here, it jumps to 1. Like 1.1, 1.2, 1.3, the ceiling function is, 0, 1, 0, 2, 0, 3, the ceiling function is 1. 1 is 1. Now, once you go a little bit beyond 1, like 1.1, 1.2, 1.3, it jumps to 2. and then here it jumps to 3, and so on and so forth. Now here's starting to give you some examples now, important examples. The floor function of minus x is minus the seeding function of x, and the seeding function of minus x is minus floor function of x. Sometimes give yourself some examples to understand what is going on here, what is really being asked. So to understand the question here, I put x here between 2 and 3, so minus x would be between minus 3 and minus 2. Now, x, the seeding function of x is 3. The floor function of x is 2. Look at minus x now. The floor function of minus x is minus 3. And the seeding function of minus x is minus 2. Now compare these two now. Compare these two here. And you see that the floor function of minus x is minus the seeding function of x. And the same thing goes for the seeding function. Now, how do you prove this? First of all, if x is an integer, then those equalities are true, because basically when x is an integer, all these brackets are gone, and you see how these are satisfied. Now, we are going to assume now, or suppose x is not an integer. So when x is not an integer, I'm going to put x between n and n plus 1. I'm just going to compute now all the terms I need. I need the floor function of x is n. The seeding function of x is n plus 1. Now take minus x. Minus x is between minus n minus 1 and minus n. So now what is the floor function of minus x minus n minus 1? Which is minus the seeding function of x. And now the seeding function of minus x is minus n. And minus n is minus the seeding function of x. Minus the seeding function of x. Now this is a very important property that we are going to be using quite a bit in this lecture. If you have any x, any real number x, and any integer k, x plus k, the floor function, is the floor function of x plus k. And the seeding function of x plus k is the seeding function of x plus k. It's as if you're taking this and getting it outside of the bracket. You're taking this and getting it outside of the bracket. To understand that, you can see in this example, square root of the floor function of 2.7 plus 10 is the floor function of 2.7, and you add 10 to it. So the floor function of 2.7 is 2 plus 10. Here you have 12.7, the floor function of 12.7 is 12, and they're equal. The same thing for the other for these other examples. Now, how do we prove this properties? Is very simple. Now, if x is integer, then those are equal because the brackets really are gone, and those are equal. So there's straightforward. Now we're going to suppose x is not an integer. So when you say x is not an integer, you put it between n and n plus 1. And let's do some calculation. Now, what's the floor function of x? Is n. What's the seeding function of x? Is n plus 1. Now, I need x plus k. X plus k, so I add k to both sides. I add k to both sides, this side and this side. So x plus k will be greater than n plus k, less than n plus 1 plus k. So this one here actually is n plus k plus 1. So n plus k is between two consecutive integers, n plus k and n plus k plus 1. Now I can compute the floor function and the ceiling functions of n plus k. So the floor function of n plus k is this. Okay, and you notice that n plus k, so what is the floor function of x plus k? That's the left-hand side, okay? That's the left-hand side. What's the right-hand side? The floor function of x plus k, because floor function of x is n, see? Plus k. So the left-hand side is equal to the right-hand side. The same thing now, what is the ceiling function of n plus k? Is n plus k plus 1, n plus k plus 1, n plus 1 plus k, see? So, and n plus 1 happen to be the ceiling function of x plus k. So we proved these two properties. They're very important, and you will see we are going to use them quite a bit in this lecture. Here's a question. Is the floor function of x plus y and the floor function of x plus the floor function of y, are they always equal? Now you can find the examples where they are equal, but they're not always equal. The answer is no. And then what we do is we find a counter example. Here I'm giving this counter example, but I want you to find your own counter example. There's a whole bunch of them. So if x plus y is equal to x is equal to y to equal to 0, then x plus y will be 1. The floor function will be 1. The floor function of x is 0. Floor function of y is 0. You add them, you get 0. You get 0. And this 0. And this is 1. They are not equal. Another question. Is the absolute value of the floor function of x, is it the same as the floor function of the absolute value of x? Again, the answer is no. And you can give a counter example. Here I give you here x equals to minus 4.3. So when you take the minus 4.3 here and take the floor function of it is minus 5, you take its absolute value will be 5. But if you take the absolute value of minus 4.3 will be 4, and the floor function of 4 is 4. And you see 4, 5, they are not the same. Another question, the floor function of xy and the floor function of x times the floor function of y, are they always equal? Again, the answer is no. Here's an counter example. Here I take x equals y equals 1.5. So when you multiply x by y, x times y, you get 2.25, and the floor function will be 2. But if you had what is the floor function of x is 1, the floor function of y is 1, 1 times 1 is 1. Again, C2 is not the same as 1. They're not equal. Now, what is the ceiling function of the floor function of x for any real number x? Now remember, this is an integer, so the ceiling function of an integer is itself. So you get this as an answer. Now here's another example. Show for any real number x, 1 plus floor function of x minus ceiling function of x is 1 if x is an integer, and 0 if x is not an integer. So this here is 1 when x is an integer, and 0 when x is not an integer. Well, it's very simple, because if x is an integer, the brackets are gone here, and x minus x is 0, so you get 1. Now the question is when x is not an integer. So again, x is not an integer. See, I put x between n and n plus 1. So now what is the left-hand side? The left-hand side, what is 1? Is 1. plus floor function of x n minus seeding function of x, and you see the answer is 0. Now, here is another example. We need to show that if x is a real number, then floor function of 2x is equal to floor function of x plus floor function of x plus 1/2. Now, I just want to remind you about some notation. When we say x between n and n plus greater or equal than n and less than n plus 1, it's the same as saying x belongs to this interval, closed on this side and open on this side. Okay, that means between n and n plus 1, n is included, n plus 1 is not included. Now, the problem here is you have, because of this 1/2, what happens if x is in this area here? If x in this area here, when you add half to it, you will still in this interval, and the floor function will be n. But when x is in this area here and you're adding half to it, it jumps to here, and then the floor function will be n plus 1. That's why we are going to distinguish two cases. Case 1 is here, x between n and n plus 1/2, and the other case, x between n plus 1/2 and n plus 1. Now, this way I cover all the values of x between n and n plus 1. So this is x. Now you find 2x. You multiply this by 2, you get this, very simple. Now I have this and I have this. I can now compute the floor function of 2x is 2n. Floor function of x is n. Now I'm adding to x 1/2. I'm adding to x 1/2. So I am now here. When I add 1/2, I am in this situation. When I'm adding one, I am here now. When I add 1/2, I'm going to still be here, and the floor function will be n. Now you add these two, you get 2n. You get 2n here, and they're equal. Now we move to the second possibility. X is in this area here. Okay, so again you find 2x, it will be this here. Now what is the floor function of 2x? Is 2n plus 1. You can see that right here. 2n plus 1. That's the floor function. Now what is the floor function of x? X is here, floor function of x is n. Now, x plus 1/2, here's the problem now. When you add 1/2 to this, it's going to go out that way. And then when you take the floor function, will be n plus 1. And plus n, 2n plus 1, 2n plus 1, they're equal. Now here's another example. Now show that if x is an integer, then seeding function of x minus 1/2 is equal to the floor function of x plus 1/2 is equal to x. So this is really simple, because here's x is right here is an integer. So x plus 1/2 takes you to here. X minus 1/2 is here. Now if you take this x minus 1/2 and take the seeding function of it, it takes you back to n. If you take here x plus 1/2, this one here, and take the floor function of this, it takes you back to n. It's very simple. Now, if x is in the middle, is n plus 0.5, n is an integer, then these are not equal. See, this is not equal. So Again, now is x is right in the middle here. See what I did? X is right here in the middle. When you add 1/2 to it, you get to this point. And when you subtract 1/2 from x, you get to this point here. And obviously now the ceiling function of this is n. And the floor function of this is n plus 1. So they're not equal. Now, example 11, show that if x is not equal to n plus 0.5 for any integer n, then this will be true. Then this will be true. So now the situation is here I have two possibilities. I have this or I have this. So in this case here, I put here's x. This is not included. This is not included. This is not included. Okay? So x is between n and n plus 0.5. And you can see now what is the left-hand side. This one here. X minus 1/2 ceiling function. When you take x minus 1/2, it takes you to here. Ceiling function is n. Look at the right-hand side, x plus 1/2. X plus 1/2 takes you to here. The floor function will be n, so in both cases is n. And you can do the same thing for this situation, very straightforward. Now, show that if x is a positive real number, then the floor function of the absolute value of the floor function of x is the floor function of the square root of x. Now, again, if x is an integer, this is true. This is straightforward. This is true. Now, if x is not an integer, so x is between n and n plus 1. So I put x here between n and n plus 1. Now I'm going to consider k square less or equal than n, the largest perfect square less or equal than n. Okay? Now in this case, square root of x will be between k and k plus 1. Also, the square root of n will be between k and k plus 1. Now, all what you have to do is find the left-hand side and the right-hand side. Look at the right-hand side. The right-hand side here is the floor function of square root of x. Okay, square root of x, floor function is k. So that's, we did that. Now we need the left-hand side. We need this here. So the floor function of x is n. Floor function of x is n. Now the left-hand side is the floor function of square root of floor function of x is the floor function of square root of n, because the floor function of x is n. And what is the floor function of square root of n is k. And in both cases they are equal. Now this is similar. I will leave it for you to do, but I recommend that you do it first and then you come and look at the answer if you have some problems. Here's another example. Show that if x and y are real numbers, then the floor function of x plus y is greater or equal than x, floor function of x plus floor function of y. Now, obviously, if x or y is an integer, then this will be easy to prove. If x or y is an integer, then there's no problem. Now, if both x and y are not integers, if both of them are not integers, here's what I do. I put one of them here between n and n plus 1, put the other one between m and m plus 1. Make sure don't use this n here and n at the same time. They could be in two different intervals. So now from this directly, you can see floor function of x is n, floor function of y is m, and the right-hand side is n plus m. We got the right-hand side now. We need to work on the left-hand side. We need to work on the left-hand side. So I add these x plus y, and then x plus y is between n plus 1, m, and between n plus m plus 1 plus 1, which is n plus m plus 2. Now, I'm saying that in this situation, x plus y, the floor function of x plus y, will be either n plus m or n plus m plus 1. It depends up where is your x plus y. Is it in this interval here, or is it in this interval here? And you see, that means the left-hand side is greater or equal than the right-hand side. And actually, when it's not equal, it will be greater by only 1, This is similar, you can do it on your own. The seeding function of x plus y is less or equal than the seeding function of x plus the seeding function of y. Here's another example. Show that the floor function of n minus 1 over 2 plus 1 is equal to the floor function of n plus 1 over 2. So what I do here is I took this and called it x. Then when you add 1 to it, the n plus 1 over 1/2 is x plus 1. So now you are asked to prove this. And this is true because what happened is x, this one here is an integer. We take it outside. That's all what we did. Now, this is an interesting example. For all values of x between 2 and 3, for what values this quantity is the smallest. Now, you notice that when x is 2, you get here, on top here, you get 2 plus 2, 4, divided by 2, 2, 2 minus 2, you get 0. When x is 3, 3 plus 3, 6, divided by 2 is 3. 3 minus 3 is 0. So when x is 2, it's 0. When x is 3, it's 0. So now I need to have x between 2 and 3. You make some calculation and you find this is equal to x minus 2.5. So this function here is equal to x minus 2.5. So if you draw this function, you find this graph right here. So at 2, it's 0. At 3, it's 0. As soon as you move a little bit here, it drops to -5. It will not get to the point -5, close to -5. And that's the smallest. And then it starts increasing. So all what you have to do is add an epsilon amount to x to get a very small number. So for example, the value is minus 4.99999 minus 0.4999 when x is 2.000001. So it will look very close to -5, but it will never reach -5 because it's 2 when it's 0 when x is 2. Now we are using solving these algebraic equations that involves seeding function. So prove that n squared over 4 seeding function is equal to n squared plus 3 over 4. So when n is odd, see, n is odd. So now what you have to do is when n is odd, n means 2k plus 1. Find n squared, find n squared plus 3. Now, left-hand side. Left-hand side, you are taking this and divide it by 4. When you divide this by 4, again, look what happened is this is an integer. I'm going to get it outside of the bracket, outer plus seeding function of 1/4, which is 1. So that's your left-hand side. The right-hand side is you take this one here and divide it by 4. And the seeding function, that's an integer, it's itself. And you see how they are equal. Here is, we are solving now solution. Find all solutions to the equation. Now, if x is integer, then you have to solve x is equal to 2x minus 3, and easily you can find x to be equal to 3. Now, if x is not an integer, so x is between, we did the same technique, between n and n plus 1. Let's replace this equation. Now we know an x between n and n plus 1. So the seeding function of x, the left-hand side here, you see, is n plus 1. And here you have two times the floor function of x. Floor function of x is n, so that 2 times n minus 3. When you solve this equation, you find n is equal to 4. So now all the solutions are x3 or x between 4 and 5. And you can check your answers. Just take 4.2 and see what happens. You find the left-hand side is equal to the right-hand side. The last example here is show that for any real number x, floor function of 3x is floor function of x plus floor function of x plus 1/3 plus floor function of x plus 2/3. Again, like I did before, I'm going to put x between n and n plus 1. When I included here x greater or equal than n, so I also included in this demonstration the possibility that x is integer, so I don't have to distinguish that case. It's already included here. So now this is the same as x in this interval. So now I know x is going to be here between n and n plus 1. Now the problem here is sometimes I'm adding 1/3, sometimes I'm adding 2/3 to the floor function. So it depends. If my x is here and you add 1/3 or 2/3, you are still in this interval where the floor function will be n. But if your x is here, you add 1/3 and you add 2/3, you're outside here, then the floor function will be n plus 1. That's why we are distinguishing 3 cases. This case, this case, and this case. So what happened is x between x in here, or here, or here, because I have to cover all the values of x between n and n plus 1. So in this case here, you multiply by 3 because I need 3x. See? You get this. Now, what is the floor function of 3x? Is 3n. What is the floor function of x? Is n. Now, I am here now. If I add 1/3 or if I add 2/3, I'm going to still be between n and n plus 1. That's why the floor function will be n here, and n here. When you add these 3 together, you get 3n. Now you do the second situation here. Now your x now is here, somewhere here. Okay? Now, look at here, 3x is this one. So what's the floor function of 3x? Is 3n plus 1. So I have that. That's the left-hand side. I'm working now on the right-hand side. Now remember, remember now is okay, now floor function of x. Now x is here. The floor function of x is again n. X plus 1/3 is here. The floor function again is n. But now x plus 2/3, you're outside here. The floor function is n plus 1. So if you add these three, you get 3n plus 1, which is this one here. Now the last case now. The last case, x is here. Okay, so you multiply by 3, you get this. Now the floor function of 3x is 3n plus 2, see? Now, x is here. Floor function of x is n. Now I'm adding 1/3. I'm outside now. The floor function is n plus 1. Adding 2/3, I'm again in the second interval here. And the floor function is n plus 1. Now you add n plus 1 plus n plus 1 plus n. You get 3n plus 2, which is equal to this. And this is the end of floor and ceiling functions, second edition. Thank you very much and see you soon.